and today I'll be covering the Carbohydrates and Biomolecules lecture. A little bit about me. I took this course actually last year, and I took my MCAT, and I felt like this course helped me prepare a lot. And currently I'm working at UCLA as a coordinator for oncology research. So if anyone wants to reach out to me afterwards about like MCAT questions or my job, like please feel free to. I can share the slides. I might try to do that at the end of the class just because I do want to get started, if that's okay. Okay, so what are carbohydrates? Okay, so I think a lot of people want me to share the slides. I can go ahead and do that. Okay, the slide should be uploading. Please let me know if it's been received. Okay, great. So there are animations, so it might be a little messed up, but anyways, what are carbohydrates? They're sugars, and they're very important. They're a big part of the food group that we consume, and they're more importantly tested a lot on the MCAT. So the basic organic compound for carbohydrates, the chemical formula is always 1:1 ratio, and it always includes carbon, hydrogen, and oxygen. And here I have a picture of some carbohydrates broken down into categories. So the simple carbohydrates are monosaccharides and disaccharides. The common monosaccharides listed here are some that we will need to know for the MCAT and memorize the structure, but we'll get into that later. And disaccharides are two of the monosaccharides linked together via a glycosidic linkage. And then the complex sugars are the ones that there's a bunch of these monosaccharides linked together. Okay. So while I was preparing for this course, I always found it very helpful to have a terminology list. So usually I would either before class or after class come up with a bunch of terms that I thought were super useful. And these are some of the terms, this page and the next page, that I just like, it's an example of how I would take notes. And we can go over them right now. And we can also come back to them throughout the lecture. So yeah. So actually, I think we'll go through them throughout. So the nomenclature of carbohydrates are determined by the backbones. So if there's a 3-carbon backbone, there are it's called a triose. 4-carbon backbone is a tetrose, and so on. The most common carbohydrate that we encounter in the world of the MCAT would be a hexose. Additionally, you can add an aldo or a depending on if it's an aldehyde or a ketone structure, you add an aldo versus a ketose to the nomenclature. And we'll get into where the aldehyde and the ketones are. Are there any questions so far? Okay. So a monosaccharide. The basic formula for a monosaccharide, again, is CnH2n and ON. And what I was referring to back here with the aldo and the ketose is right here, if you can see with my mouse. So this would be an aldehyde. So this would have the either the prefix or the suffix aldo. So I want to make this class a little bit more interactive. So can someone tell me how many carbons are in the backbone of this structure? Perfect. 6 carbons. So when we're talking about the backbone of a monosaccharide, you always include it from the top where the carbonyl carbon is. So this would be C1, C2, C3, C4, C5, and then C6. I guess I just answered the second question, which is what is the C1 carbon? It's this one. And so the follow-up question is how many chiral centers are present here? I'm hearing 4 from Melody. Another 4. Yep, so there are 4 chiral centers. And again, a chiral center is when a carbon is attached to 4 different groups. So this would be a chiral center. Can you guys see when I hover over with the mouse? Okay, great. So this would be a chiral center, 1, 2, 3, and finally 4. How this is relevant is when you determine structures like distereomers, to determine how many stereoisomers of a structure there are, you use the formula 2 to the n. So in this case, there would be 2 to the 4 different ways of describing the structure. So 16 total. Does anyone by chance know what the anomeric carbon is?
Double O.
Yep, someone just said the C1, and that's absolutely correct. So the anomeric carbon is referred to as the most oxidized carbon. So it's the carbonyl carbon, and this will come into play a bit later, but I'm really glad that people do know what it is. And finally, how would you determine the name? I can go back to the previous slide to just show the nomenclature, but if someone is able to put it into the chat box. So the anomeric carbon is right here. It's the first carbon, it's on the carbonyl carbon. Does that make sense? Okay, great. Yep, Melody, this would be an aldohexose. So the reason it's an aldohexose is because the first carbon is an aldehyde, and then there are 6 carbons, so therefore an aldohexose. What would happen if this was a ketone? Yep, perfect. It would be a ketohexose. Oops. Okay. Can you explain? Yeah, sure. I can explain the chiral centers. So what a chiral center is when a carbon is attached to 4 different groups. So the carbon right here is one attachment is the hydrogen, one attachment is the hydroxyl group, and the other attachment is the aldehyde, and then the rest of the chain. And so that forms 4 distinct connections. Same here. There's an aldehyde, there's a hydroxyl, a hydrogen group, a group over here that is distinct from the group down here. This would not be a chiral center here because this carbon is attached to only 3 groups. So there's 2 bonds to this oxygen, 1 bond to this hydrogen, and 1 bond to this carbon down here. Does that make sense? Yes, the attachments, wait, one moment. Yes, so the attachments, when I mentioned attachments, it's what is coming off of the chiral carbon. So the carbon, for example, this would be a chiral carbon. And the attachments would be a hydrogen group, a hydroxyl group, this aldehyde. Does that make sense? Okay, great. All right, so moving on. So these are the common 6, one moment. Sorry, so these are the common 6 carbon sugars that we need to memorize for the MCAT test. And these are presented in a Fisher projection. So that means it's a 2D representation of a 3D image. So here we have D-mannose, D-glucose, D-galactose, and D-fructose. Does anyone know why, what the alternative to a D group sugar would be? Or sorry, D sugar? Yep, L. Perfect. Does anyone know why D is the more prominent one versus L? Yep, so I guess it would be, I guess that's like did the chicken come first or did the egg come first kind of question with the enzyme. It's our body produces D sugars and therefore we only have enzymes that break down D sugars. So the most common, the sugars that we have in our bodies is the D one. So I, while taking this class last year, I learned these quick ways of remembering the structures, which have actually, like I still remember them to this day. So the way the D-mannose structure I remember is using my right hand, I make a gun thing, like a, yeah. So that will include these two OHs on the left side. And it's important to note if the hydroxyl groups are on the left side versus the right side. And then with glucose, we have a bad word. However, it does help us remember how to draw the structure of glucose. Yep. And then galactose, the way I imagine galactose is kind of like a rocket ship, because like you have your two, like your middle finger and your ring finger on your right hand pointing to the left. And then finally, fructose is a little bit harder to remember because because it's a ketone. So here is the ketone part of it where there's a double bond to the to the carbon, and then there's no hydrogen groups, there's 2 R groups. This one is similar to glucose. So this one is similar to glucose, and that's the way I remember it. Does anyone have any questions about the structures or how to remember them? Yeah, so this is definitely a drawing that I got from the book. So thanks, Todd's daughter. Okay, does the structures make sense? What would L structures look like? Okay, sure. So the difference between D and L are that they're enantiomers. That means that at every chiral center, the OH and the H would be on opposite sides. I'm sorry, I don't understand what's going on here. Melody, what are you saying? Hydroxyl on C5 is the opposite side for D and L? I think the difference between D and L is that the sugars switch all stereo centers. Does that make sense? Yes, of course. Okay, great. And then here we see something called an epimer of glucose. So that gets into more of the terminology, and I'm just going to go back to the slides back here. And this is where having this really saved me, especially in this lecture, where there's a lot of nuanced terms to define like basic things. So an epimer means that the positions differ at one chiral carbon center of only the backbone carbons. So going back here, I'm going to explain what that means. So the backbone carbons are the carbons that have stereo centers. So the carbon right here, 1, 2, 3, and 4. So technically there can be 4 different epimers of galactose. And so does that make sense when I say the backbone? So it would only be carbon. So this would be C1, C2, C3, C4, C5. Okay, great. So a C4 epimer of glucose means that the 4th carbon is different in, yep, Jonathan, C2 to C5 is the backbone, perfect. So the 4th carbon switches in orientation. So when we look here, this would be C2, C3, C4. Over here, we see that the OH is on the left side. However, in glucose, we see that it's 1, 2, 3, 4, and it's on the right side. So therefore, it would be a C4 epimer of glucose. So I have a quick question over here. How do mannose and glucose differ then? How would you determine their epimer relationship? Oops. Sorry, I didn't mean to reveal the answer. But yep, so it would be a C2 epimer. So we look over here, mannose and glucose, and we see that the difference is this carbon right here, which would be the C2 carbon. The OH over here is on the left side versus on glucose, it's on the right side. Are there any questions before I move on to the next slide? Yes, Jonathan? I think that would just describe it as a distereomer as opposed to an epimer, because an epimer would only be at one specific carbon. Yep. And it's to determine the relationship between 2 sugars. Okay, so finally we have the 5 carbon sugar, which is ribose. And this comes into play a lot during DNA synthesis as well as different reactions. So ribose is very easy, that it's a 5 carbon sugar, and it's all of the hydroxyl groups are on the right. So I'm just going to move on. And then here I have a little slide to determine D versus L sugars. And if we see here that the D glucose has, it flips at all stereocenters between D and L. And then to determine if it's D versus L, you look at the chiral center on the very bottom, and then if the OH group is on the right, you would say that it's a D sugar. And then if it's on the left, you would say it's an L sugar. And the way I remember this is I have this trick. It's called Dr. Loser. Oh, okay, perfect, Melody. I'm glad that we clarified that. So Dr. Loser is a great way to determine D versus L sugars. And so if it's on the right side, the hydroxyl group, it'll be D. Does that make sense? Okay, perfect. Question, how many possible aldohexoses are there? Perfect. Does someone want to say why? Yep. So there are 4 stereocenters, and because there are 4 stereocenters, the way you do it is 2 to the power of the number of chiral centers, exactly how Brooke wrote here. So 2 to the 4 is 16, and here I have only 8 of them, and the other 8 come from L-glucose or L-galactose or L-idose, which would just be all of the stereocenters reverse. Okay. I have another question here. What is the relationship between D-galactose and D-glucose? And I can go back to the slide just because we don't have, oops. I'm not sure if everyone has the structures memorized yet. Okay, so this is the slide, and then I can go back to the question as well. Yep, so the answer is C4 epimers. And again, it's because C2 through C3 look the same. And then C4, we see that the H and the OH are the OH on glucose is on the left, and then the OH for galactose is on the right. Yeah, I know the C1 and the C2 is very confusing, but you got to remember that aldehyde or the carbonyl carbon counts as C1. Okay, great. Are there any more questions? Okay. I'm going to move on. So the next thing that we have to tackle is the Fisher to the Haworth. I always want to say Hawthorne. I'm here in LA, so I don't know if people know where Hawthorne is, but it's Haworth. Yeah. Okay. So the difference between the Haworth and the Fisher is that the Haworth is more cyclic. So it has more of a 3D representation of how the sugars would look like. And then the way that these are formed is that the hydroxyl group right here of C5 attacks the carbonyl carbon to form a hemiacetal or a hemiketal. Does anyone know what a hemiacetal or a hemiketal is? Okay, that's fine because this was something that would always confuse me. So I have a picture of, I don't know how to exit this. I will just go to the picture because it's something that would always confuse me as well. So this is a hemiacetal, and what that means is that the carbon has an OH group, and one ether group and one R group and one hydrogen. And then how this is different from a hemiketal is that a ketal will have, I'm sorry, I don't have a picture of it, so it's a bit confusing. Let me just see if I can pull up a picture and send it. I don't know how to, but I'm sure you guys can Google the way a hemiketal looks. But so when I say hemiacetal, this is what I mean, where there is one OH group, this hydrogen here, and the OR and the R. Oh, here's a hemiketal. I'm so sorry. So there's two R groups here. So for a hemiacetal, it would be the aldehyde version, which is why there's a hydrogen. Does that make sense? I'm so sorry for confusing people. All right, so I'm just gonna go back here and open up the chat. Sorry, that's my foster puppy. He has a bit of a kennel cough, so sorry about that. Oh, I'll get back to the reducing versus non-reducing sugars in a little bit, just because it's I have like a couple things I want to bring up, but I just wanted to go back here and just talk about the Haworth structure, if that's okay. Oops. Okay, so what we see here is, again, that the C5 hydroxyl attacks the carbonyl carbon and forms a cyclical structure. So we see that the way that these are numbered is that the oxygen is right here, and then it's C1, 2, 3, 4, and 5. So this creates more of it's not a 6 carbon ring, but it's a 5 carbon ring plus an oxygen. Yes, it's always in this. So this will always be C1, then this will always be C2, C3, C4, C5, and so on. And the way we determine how these side groups are positioned, on the cyclical ring is depending on if they're on the left side or the right side. So if it's on the right side, it would position down. And then if it's on the left side, it would position up on the cyclical structure. Which one is the carbonyl in the ring? Yep, just one moment. Let me just. So the carbonyl would be the C5 attacks. This is the carbonyl carbon. I'm pretty sure. Can you point where the C5 ends up? I'm having trouble. Yep. So C5, this is the carbonyl, the hydroxyl group that's attacking this group. So this CH2OH group is right here, CH2OH. And it's on, this is carbon 5. And then, does that make sense, Aditya? Perfect. And please ask me. Yes, Stephanie, that's correct. So C1 is right here, this group, C2, C3, C4, C5. And then I guess this is the CH2OH group, the 6th carbon. Jonathan, I'm not really sure. I don't have a pen, so I'm not able to draw it, but I know that in the book that there is a visualization that it helps to see the in-between structure. But are there any other questions I can answer about this one so far? The structure? So yes, the orientation of C1. Actually, that would be the next slide, because that one's a little bit, not tricky, but it has its own rule. I'm just going to go back to C5 really quick. So C5 helps determine if it's a D sugar and L sugar. So if it's if the C5OH is on the right, then it's a D sugar and it would face up. So we see C5 is on the right here, and it's facing, one moment. I'm just going to close out of the chat really quick so I can just see the full picture, if that's okay. Okay, I'm just going to go to the next slide and then come back because I think there's a lot of questions about C1 popping up. So how do we determine the C1OH position? And that's right here on carbon 1. And if it faces up, then it's known as a beta position. And then if it faces down right here, it would be an alpha position. And the thing is, you can't really tell if it will be up or down just as is because it depends on which face of the carbonyl it was attacked. So either like behind it or in front of it. And it's always given in some way in like a testing situation. So they'll say like, can you please draw an alpha glucopyranose, or can you draw the beta version? Does that make sense? Just gonna go back into the chat. Beta faces the birds. Oh, that's cool. I like that. Alpha faces the ants. Hey guys, that's really good. I actually have a question coming up, Aditya, to answer your question. Okay. And then back here, the C5. Oh, you're right. The C5 is both OH. The C5 carbon is both on the right, so it's facing up. It's because it's they're both a D sugar. Okay, I'm gonna pull up the question. Oh, this is another just vocabulary question. So this is the pyranose is when it's a 6, when it's like a hexagon, but the oxygen is a part of the ring instead of a carbon. And then furanose would be this structure, and this would be for like a ribose. Okay. So this would be a question that you would see on the test. Convert D-mannose to a Haworth in an alpha pyranose configuration. So here they note that it will be alpha. So do you guys want to work on this question? And please let me know if there's any questions that I can answer in the meantime. Yep, so beta is for the birds and alpha to the ants. And then the other trick I use is downright uplifting. Yeah, but it's uplifting. All right, how's everyone doing? Do they still need a little bit more time to draw out the structure? Oh, that's fine. I do have the answers coming up, so we can go over it. All right, I'm gonna flip. All right, so this is the way to draw it. So in the question, we were told that we were going to draw an alpha configuration. So because we knew that the C1OH would be facing down. And then because it's a D glucose, which is how we figure out, the way we figured that out, I'm so sorry. The way we figure out that it's a D glucose is we look at the C5 carbon and it's on the right side. And then remember like the doctor loser acronym, I guess, it would be a D sugar and therefore it's facing up. And then for the C2 through the C4 carbons, the way we draw those is the downright uplifting method. And then also another quick note is for D sugars, the CH2OH group is always going to be facing up. And the alpha versus beta. So if it's beta, that means it'll be cis. So beta configuration means that the OH will be facing the birds and therefore it'll be a cis configuration because the C5 and the C1 carbons look at each other up there. And then if it's alpha, it will be trans. Does that make sense? Does anyone have any questions? Yep, I think my first sentence was about CH2OH, is that correct? So CH2OH, the reason it's facing up is because we're dealing with a D sugar here. So the rule is back here. So if the fifth carbon is on the right, then the D sugar, then it's a D sugar, which means that it'll be up. So C5 again, 1, 2, 3, 4, 5. So this is C5 right here, and this is facing up. So if it was an L sugar, then this group would be facing down. Okay, great. Did that make sense, or would you like for me to repeat? Okay, perfect. Great. All right. So yeah, you guys have these slides. The way that I did this was I would just copy over all of the sugars over and over again and just try to memorize it that way. Unfortunately, this is a big memorization one. And these are all of the projections in the cyclical form. And I think a good way to remember them maybe would be to use the glucose one as a reference and see how it compares to it. So see how the mannose one compares to glucose. And then you can determine, so the C1 for both of them are the same, C2 is opposite, C3 is the same, so OH is on the top here, and then C4, OH is on the bottom. So the relationship between mannose and the glucose would be that there's C2 epimers, which again means that it's different at one carbon chiral center. So did that make sense? Okay, great. And then you can do those for the other ones as well. Okay, so the next thing we're going to do is to convert from the Hayworth to the chair configuration. So just as a, I guess, a background, I'm not sure how much you guys did with chairs, but the basic guidelines for a chair conformation would be that equatorial are in like the M and the W line is what I call it. And then axial is always facing vertical, like longitude lines on a globe. So the M is right here. So I see M, and then normally there's like one over here, but because it's an oxygen group, that doesn't exist. And then the W is down here. Do you guys see that? I hope. Otherwise, like I'm sure people know what equatorial and axial are as well. And then this carbon is again the C1 carbon. So it's named the anomeric carbon again. And then the way you translate from Hayworth to chair is that things that are facing up go up, things that are facing down are facing down. And then having your attachments or your additional groups in equatorial position is what's most stable. All right. So this is what glucose looks like in a chair conformation. And it looks super overwhelming, except there is a trick. The beta formation for the glucopyranose is that all substituents have equatorial orientation. And then for the alpha, the substituents are all equatorial except for the anomeric OH. So that's like a easy way to remember. I'm gonna go back. Someone just asked me a question. So the question was, are green axial and pink equatorial? And that's not necessarily true because this position right here is a axial position, whereas this one is equatorial. The most stable form is to have all your substituents be equatorial. I'm just going to walk through the W and the M again. It's just the way that I look at it. So this is the M. So it starts right here with the pink, then goes down here with another pink, and then the oxygen group, and then it's a W on the bottom. So that means this is equatorial, then this pink group is equatorial. The easiest way to probably remember this is also that axial will always be facing like in a straight way, in a vertical line. Does that make sense to whoever asked? Okay, perfect. Oh, I'm glad. Okay, all right. Axial is vertical lines on the chair conformation. Yep, perfect. So it'd be this pink right here, then this green, then this pink down here. And so they're facing either straight up or straight down. Oh, I'm so glad. Okay, great. Okay, so the easiest way, again, to remember the glucose, the beta configuration, is that everything is equatorial. So that means that this structure is super happy. So this is the beta structure because it has all of the big groups in an equatorial position. So therefore, it's not colliding with anything. So the axial, there are things that are axial here. So again, the straight up and down ones, however, they're hydrogen. So that doesn't really matter because hydrogens are so much smaller than, for example, this OH group. And then in this, the alpha position is, again, the difference between beta and alpha is the C1 carbon. So C1 is right here, and this will always be C1 unless noted differently. That's like the common practice. So C1, C2, C3, 4, 5, and then the oxygen group. So yeah, so the difference between beta and alpha is the C1 anomeric carbon. Then we have the rest of them, the mannose, the gluco, which one is that? I think I just drew, yeah, I drew the glucose one again, I'm sorry. And then galactose. There is a quick way to remember the other ones as well, the mannose and the galactose, and it's 2 man for a gal. So that means that it's mannose is a C2 epimer of glucose, and galactose is a C4 epimer of glucose. So everything else is the same, but besides those positions, so we see here the mannose is different at the C2 position. And then for galactose, it's 1, 2, 3, 4 at the C4 position. So there are a bunch of little tricks like that that help keep me sane throughout my MCAT. So one of them was, again, Dr. Loser, downright uplifting, and 2 man for a gal. So yeah. Does anyone have any questions right now? Or should we move on? I'm glad you like the mnemonics. And yes, I'll explain the 2 man for a gal thing again. So basically, I think I'm gonna go back to, where is it? Here. So 2 man for 1 gal. So mannose and glucose, the difference between these two is the C2 position. So the C2 position, again, this is C1, then this is C2. So the OH over here is on the left and the OH over here is on the right. Everything else is the same between mannose and glucose. So therefore, mannose and glucose are C2 epimers. And then the difference between glucose and galactose would be the C4 position. So C1, 2, 3, 4, this position over here, the OH is on the left side here, and then the OH, I'm so sorry, on the right side here, and then the OH here is on the left side. So that's why the mnemonic 2 man for a gal is the relationship between glucose and the 2 other sugars. Okay. Yeah. I guess it's just people trying to cope with how much content there is in biology. Okay. All right. So again, these structures, They look a little intimidating right now, but once you break down and remember the C2 and C4 rule, it'll be pretty easy because then you only really have to focus on the beta glucopyranate. I don't know how to say this. I'm so sorry for saying it wrong the entire class. The key difference is the C2 position and the C4 position, and everything else is similar. All right, so of course, there's going to be the addition of monosaccharides to form either disaccharides, oligosaccharides, or polysaccharides. And the linkage between two monosaccharides is called a glycosidic linkage / an acetyl linkage. And the way it's formed is via a dehydration reaction of the two hydroxyls. So this is maltose. So it's two gluco, one moment, two of these. And the OH that I'm referencing is this OH, by the way. And then the key linkages that we need to know for the MCAT are the alpha 1,4 and the beta 1,4 linkage, which are shown here. So the way we determine an alpha 1,4 linkage is again by counting the carbons. So this is a C1 carbon, and it's linked to the C1, 2, 3, 4. Therefore, it's the 1,4 linkage. And the reason it's alpha is because it's trans. So the O is not facing the same way as this group here. Does that make sense? So the O is facing down and the group right here is facing up. And that's why. So both sugars need to be trans. I'm not sure if that's a hard, to be alpha. I might have to get back to you on that to give you a conclusive answer, but I think that is true. So Stephanie, I'll either if you could email me or if I could email you. Yep, I can explain the trans again. So here it's an alpha 1,4 linkage. So what we're looking at is this group here, which used to be an OH, and this group here. This group is facing up equatorially, and this group is facing down on an axle. It doesn't really matter if it's on an axle or equatorial, but it matters that it's the direction it's facing. So either up or down. Does that make sense, Naomi? The second one. Okay, there are a couple of questions. I'm just gonna just look back here really quick. I think, Melody, you're right, where it's only the anomeric carbon that we take into to account to name this part right here, the beta. So this is the galactose pyranosal sugar. And the reason it's beta is because it's facing the OH here, and the CH2OH group would be facing in the same direction. So therefore it'd be beta. And then here the groups are facing in opposite direction. So it would be alpha, because it's trans. However, the linkage is called beta glycosidic linkage. And I'm thinking it's because of the first sugar. Does that clear up? Any questions? Okay, great. All right. So moving on to what's known as a reducing versus a non-reducing sugar. Can anyone tell me, like, visibly what the difference between this D-glucose and methyl glucoside is? And feel free to like unmute yourself as well if you want to say it. So the key difference is this group right here and versus the hydroxyl. Yep, a couple of you guys got it, so good job. And the difference here is the OH here will be reactive and it will try to create a linkage like this. However, the fact that this OCH3 forms at the anomeric carbon, it prevents it from forming a linkage. Thus, it's a non-reducing sugar. So when it's a hemiacetal, it means that there is a free OH on the anomeric carbon, which is again the C1 carbon, and that will react to create a glycosidic linkage, or it's also called an acetal linkage. Whereas something that's just an acetal or a ketal, it won't react to create a linkage. And then the difference between hemiacetals and acetals are between these two images, where there is an OH group. However, in this group, there are two ether groups on the same carbon. So an ether group is an OR group. Yep, so hemiacetals are reducing sugars, and hemiketals are also reducing sugars. So this would be a hemiketal. I don't know why I'm saying this so wrong, but this would be a hemiacetal because there's a hydrogen right here. And then these would just be acetals. Yep, so we're seeing what's on the anomeric carbon. There was just a question from someone as a direct message, and I'm not fully understanding what the question is. Yes, so for it to be a reducing sugar, it needs to have a hemiacetal group in the C1 position. However, if it's not, then it will be a non-reducing sugar. All right, I'm gonna flip to the next slide, and I have a question here, and it's, what is the linkage that is shown here? Okay, I'm just gonna give maybe one more minute. All right. So the answer is A. And I thought because this was in a Hayworth projection that it would confuse people, but it did not. So really good job. And again, so C1, C2, C3, C4, C5. So it's alpha 1 here because it's trans positioning, and alpha sees ants, and alpha happens to be the trans position as well. And then C1, C2, C3, C4. So therefore it's an alpha 1,4 linkage. And this is called maltose, which is two glucose monosaccharides coming together in a linkage. And this will be a reducing sugar because there is one free anomeric carbon right here that can react. Does that make sense?
Sorry, could you repeat that last part again about the reducing sugar?
Sure. So because there is a free OH group here at the anomeric carbon, it is a reducing sugar. Does that make sense?
Yeah, thank you.
Perfect. Okay. And then the anomeric carbon here is tied up in the bond. So we just need one free one. All right.
Was there a difference between options B and C?
Option B
Are,
and C.
are those the same thing?
Option C would be further describing. So the second one, the second sugar technically could be an alpha or a beta, but option C is specifying that both sugars are beta.
Okay, got it.
All right. And I'm just gonna save the acetal and the ketal questions for the end of the lecture. I think some people are ready to move on, but I'll be free for half an hour to an hour after the lecture, so we can definitely talk more about it. Okay, so the last thing that we're going to talk about in the carbohydrate section is polysaccharides. So polysaccharides are linkages of multiple monosaccharides together. And the three key ones here are cellulose, amylose, and glycogen. Amylose are belonging to plants for energy storage, and glycogen are for human storage of glucose. And the key difference between glycogen and amylose is that glycogen is allowed to have additional branching in the 1 to 6 linkage, whereas amylose does not have any branching. However, both of them are alpha 1,4 linked. And then for cellulose has a beta 1,4 linkage, and that is unique because you would need a beta glucosidase in order to digest it. However, people do not have the beta glucosidase. Humans only have alpha glucosidase, so we're unable to digest cellulose. And additionally, there's no branching involved in cellulose. All right. Are there any other questions for polysaccharides? Okay. All right, so the last thing that we're going to talk about is something called terpenes, which are aromatic compounds, and they all have the base formula of an isoprene. So this is an isoprene that we see right here, and they're always 5 carbon chain, and they're broken down into these isoprene units. And if there are multiple, like 2 isoprene units together, then it is called a monoterpene, and it's 10 carbons long, and then so on and so forth. And normally the monoterpenes, and then these, I can't pronounce it, I'm not going to try, the 15 carbon length ones are for plants, and they function as pheromones. And usually the bigger terpenes are in animals. And then when it's a terpenoid, it's a terpene with a functional group. So it could be an OH group or a phosphate group, or so on and so forth. Oops, okay. So what kind of terpene would this structure right here be? Does anyone have a guess? I see monoterpenes. And how did you come to that conclusion? Yep, so it's 10 carbons, therefore it's mono. And then before I show you guys how this is broken down, could you visualize how the isoprene units are, like how the 2 come together to form this structure? Yeah, I agree. It's really hard to see it at first. However, unfortunately, this is a big MCAT question. And the way, or like terpenes are a big MCAT topic, especially recently. And the way that I got comfortable with this was just like looking at the structure, the isoprene structure, and then seeing how it's broken down. So the way that this alpha terpene is broken down is right here as shown. And the way I would count it normally is 1, so right here, whenever you have a carbon chain, you always want to count the longest part of the carbon. So carbon 1, 2, 3, 4, and you have a methyl group coming out of C2. So the way I would look at this is 1, 2, 3, 4 with a methyl group coming out of 2. And then again here, I would see 1, 2, 3, 4, and then a methyl group coming out right here. So someone had a question about 2 sets of double bonds, and that is correct. However, one of the double bonds reacted to create a cyclical structure. I think it is similar to the Diels-Alder reaction. I just don't have that memorized anymore. So I can look that up and answer that question. Oh yeah, it would be similar to the Diels-Alder question. Sorry, Diels-Alder reaction. Okay. Does anyone have any other questions before I move on to the next slide? I'm gonna go more into details. I will show you the structure for that, Mo. Okay, that's coming up after this slide. So the way that they're synthesized is actually using this isoprene unit and then adding a pyrophosphate across the diene. So this diene helps to add this pyrophosphate unit, and then these 2 are what's the word? Can someone help remind me how you relate these two structures where there's a double bond here and then it moves over here? I think it's isomerized. Does that sound familiar? I can't think of the word. I once this lecture ends, I will look back into it. But these two are related because the double bond just moves from the C1, C2 to the C2, C3. I think it's conjugation. I'm not sure. So anyways, down here, I've showed the reaction between two of these units. And it's that the diene reacts with the carbon on the oxygen, and it creates this chain. And I have like the reaction and further details down here. I don't remember seeing this exactly on my MCAT exam. The way I would process this information, I think, would be, what is a terpene? Terpenes have bases of isoprenes. What is an isoprene? Isoprene is a 5-carbon chain. And how do terpenes form? They form by using a pyrophosphate group. And then this kind of reaction is pretty normal. So I don't know if I would like brutally memorize this as is, but I would just remember like a double bond can react to form a long chain. So yeah. All right, so someone was asking about this earlier. So here is the C15 carbon down here. So the way that you produce all these is an isopentyl pyrophosphate reacts with another isopentyl pyrophosphate to form a mono, it's called a something G pyrophosphate, which is a C10 pyrophosphate. And then this can further react to form a monoterpene. So either this phosphate group is just a good leaving group and it leaves, or it can be substituted with another group. For example, a chlorine or an OCH3 group. Then you can add another isopentyl pyrophosphate and create the backbone for a C15 terpene. And then the C15 terpene, this one right here, can either lose this pyrophosphate again and then create this C-quitter terpene, or it can form squalene. The reason squalene is important is because that it is the way cholesterol is created, and cholesterol is a super important biomolecule within, for example, like the plasma membrane and a couple of other regulations of the body. And I've actually gone into detail here about how you can form from an isopentyl pyrophosphate to a squalene structure to linestrol to then cholesterol. And between these two, there's a bunch of like niche enzymes and whatnot that help form the cholesterol. But the big takeaway picture is that squalene is a linear molecule, and it's epoxidated by an enzyme to create a cyclical structure, which is then further modified to create cholesterol. Does that make sense? Does anyone have any questions that I could answer? Jonathan, I don't know if I could Well, the MCAT is a multiple choice question. So, you know, like you won't have to draw out this exact, this exact picture, of course, but I think it would be important to realize that cholesterol comes from a terpene origin, and then squalene can epoxidize to form this structure. No, I'm not going to try pronouncing the C15 carbon. It's very, it's only, I guess it's 10, but I've been up for a while, so I'm kind of tired. Could I briefly cover what epoxidation is? Yes, I can, but is there any other questions? This is actually the last slide. So if there's any questions related to terpenes or carbohydrates directly that I could cover, I can definitely get into that, and then we can follow up with epoxidation. So does anyone have any questions? Alexandra, are you referring to a specific structure? Are you referencing maybe this one? Which one are we talking about? This one? Okay, gotcha. Yes, so it would be one pi bond because the other pi bond was involved in the reaction. So this pi bond, oh, I'm sorry. To begin with, the isoprene unit reacts with the pyrophosphate to create a unit that looks like this. And subsequently, these are the units that react to create these guys. So that's why we only see one per unit. Does that answer your question, Alexandra? I just want to make sure, more so confirm. Okay, perfect. And then I see another question. Resulted in the cyclical. So I was doing some research about this, and it looks like that the isoprene, isopentenyl pyrophosphate, this is how these terpene products are created, but I could not confirm like 100% positive that like all terpenes are created through this mechanism. In the book that we use, this is the mechanism that was used. So yeah, so I think this would have the pyrophosphate, however, it's not completely drawn out. Okay, perfect. And then people are wanting for me to go back to slide 24. Oops. From the current slide. Okay, so the question is this a hemiketal or a hemiacetal? So this is a hemiacetal right here. And then the reason I know is because this has, I'm gonna see if I can pull up picture, and that might be a bit better. One moment. Just bear with me. I'm just gonna Google a picture of hemiketal. Okay, I found a picture that I like. How do I show you guys? Share screen. I'm so sorry, it's taking me so long. Okay, so when I say hemiketal, it means that it originated from a ketone, whereas a hemiacetal originates from an aldehyde. So all of the sugars besides, I think, fructose are aldehydes, and this is and all the other ones are aldehydes. And when I say that, I'm referencing right here. Can you guys see? So that's why I know it's a hemiacetal, because of this aldehyde right here. And then if I go back to page 24. So with this carbon group right here, there's an OH, an OR2 group, a hydrogen right here, and an R group. Okay, so C1 would have a group like C5. I think instead of this hydrogen here, it would have to be an R group. So there is a hydrogen that we don't see. That's why it's a hemiacetal. Does that make sense? Okay, cool. Did anyone else have, I know that there was another question about hemiketals and acetals that I would love to address. The reactivity of it. So the reason why hemiacetals, so this is a hemiacetal right here with the hydrogen, and this is a hemiketal, and these are reactive because of this blue OH group. Something that is just an acetal is not reactive because there is no free OH group. And that's what I was showing right here. So there is a hydrogen here, which is an R group. There is an ether. There's two ethers here and another R group, but there's no free OH to react with another sugar for it to be a reducing sugar. So this would be a non-reducing sugar. And because of this free OH group, this would be a reducing sugar. And furthermore, this would be a hemiacetal because of this hydrogen right here. Does that clarify? Yes. So for reducing versus non-reducing, it has to be the anomeric carbon. Does that answer everyone's question? Okay, perfect. Are there any other questions or about the lecture itself that I can address or clarify? Yeah, I don't have any other slides, so I just wanted to have some more time to cover any questions or things that you have to memorize for this specific unit. Oh, the epoxidation. Yep, I will. Why the MCAT can ask about terpenes? I guess they can just kind of do whatever they want. The reason terpenes are important are because they're a big aromatic compound. So that's what a lot of like pheromones and a bunch of other things come from. And oh, what they can ask, I see. I guess they would give you a structure and ask. There are a couple of examples in the textbook where they'll give you a bunch of structures and they'll ask you, is this a terpene, or what were like the base units that come from that structure. So like a question like this. Or they could give you a bunch of different structures and say, can you identify which one is a terpene? I personally have not seen any terpene questions. Like it wasn't on my MCAT, nor was it on any of like the AAMC practice questions. So my knowledge about terpenes comes from this class only. And I think the questions are really good in the textbook. Does that answer your question though?
Yeah, I think so. Can you go to the next slide though? Or the next, or so does it always have two bonds? I think that's what I'm kind of
Which,
understand.
where are you referencing the bonds? Like which bonds?
These bonds over here. So I guess this is up here. This is one unit of terpene, but to connect to other terpenes, it has to lose one of these double bonds. So if I'm looking at multiple units of terpenes, I'm always gonna assume it's gonna lose a double bond to connect to the other terpenes.
Yep.
And the unit over here. Got it.
So like here too. So we see 1, 2, 3, 4 total. However, there's only 2 in the structure.
Got it.
And then a big part of it is also like understanding that the 5 carbon rule. So like honestly, just sometimes counting the carbons. So this one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. So therefore it could be a qualifier for it to be a terpene. I know that's like a big way that Todd eliminates questions is like, hey, like if this has 16 carbons, it can't even be a terpene, so I won't even consider it as an answer.
Okay, so it really is dependent on these numbers, this formula here, or not the base formula right there, but it can only be multiples of 5. So if I get a question and I'm confused if it's a terpene question or something else, or if they're asking if it's a terpene, just count the number of carbons, first step.
And just to clarify, so cholesterol has 27 carbons, but it's because I don't know if it's I think it's classified as a lipid. Someone please correct me if I'm wrong, but I don't know if it's classified as a terpene as is, but it is synthesized from a terpene.
Okay, yeah, that makes sense. Yeah, because cholesterol is a class of lipid, but I don't think it's a terpene. But yeah, what you said makes sense, that it's synthesized from a terpene.
And because cholesterol is so important, I think just knowing that it comes from squalene and then cholesterol is key.
Gotcha. Thank you.
Terpene derivative. Okay, yeah, perfect. And then I'm still trying to figure out the epoxidation question, so just bear with me. But if there's any other questions, I would love to answer them. Oh, you figured out the epoxidation? Okay, cool. Yeah, it's just like a cyclical, you can close, it forms like a triangle, essentially, via double bond. All right, cool. Are there any other questions? I do not have an office hour scheduled right now, but if you have questions, you can feel free to reach out to me via email. And then I work 9 to 5, so I can probably schedule an office hour in the evening. And I'll put my email here. Yes. Are there any other questions? I feel like I should have, I don't know, spent longer covering some of the structures or anything. So if there are any questions, I'd love to help. How's like the class going so far? Do you guys have any questions about rough? Oh no. Yeah, it is a lot of content. I think you just have to figure out the more like important things. Like there's no way you can remember everything. One of a big info guide that I used right before my tests was the Kaplan one. I'm not sure if you guys have seen it, but it's a guide. I think it's like 12 pages long. And it was really helpful, like right before the test, to just look over it and make sure I had those things covered. But I can see if I can find it and I'll try to send it. Does anyone have any other questions? Oh, I found it. Okay, it's called the quick sheet. I can't write on the screen. I just have my MacBook right now. But if you have a question, you can email it to me and then I can draw it out and then email it back to you. Oh yeah, there's a lot of Kaplan content, but I really like this quick sheet. Yeah, of course. I think, Alexander, it comes with a lot of like practice, just like looking up different linkages and just analyzing them. And yeah, of course, guys, thank you for, this was my first class I've taught in this context. So thanks for bearing with me. Yes, this does conclude lecture. I'll just hang out until I guess everyone's ready to leave and just see if there's any other questions someone wants to ask me. And please feel free to email me. Very available via email. Jonathan, could you provide us with what questions to complete for phase one? I don't actually know. I would say try to complete phase one. The way we did it last year was we tried to complete phase one as quickly as possible to this lecture. And then phase two, I think you complete like 2 to 3 weeks after. Mm-hmm. Yep. Yep. And I think for book 7, there are like a lot of lipids and carbolipid questions. I think the chapter is about lipids, but that's where the terpenes are as well. So I'm not sure if there will be another section for lipids. I know I'm teaching another class, so that might be where I touch up more on lipids. But I think chapter 7 is the one with terpenes in it. But there are other things as well. Are there any other questions that I can answer? All right, good luck, Jonathan.